And they predicted that these models share a triple of exponents. I will talk in more detail about the exponents later, but these three exponents are 1, 1/3, and 2/3. And ever since, it has been an active area of research in the mathematics and probability community in particular. Okay, so there are many different models predicted to be in the KPZ universality class, but we will focus on one particular class of model, that of the planar last passage percolation. So there are two dimensions, one space dimension and one time dimension. So the basic setup is that we have an IID space-time noise, and among this noise, we consider paths moving forward in time. And for any path moving forward in time, the weight of that path is obtained by integrating the noise along that path. And the last passage time between 2 points is obtained by maximizing the weight over all paths connecting the 2 points. Optimizing paths, of which there could be more than one, are called geodesics. Okay, so this is the basic setup. And canonically, these models, canonically meaning under very weak conditions on the underlying noise space, these models are believed to be in the KPZ universality class. However, rigorously, it is known only for a very few special what are called exactly solvable or integrable models, where there are some remarkable bijection connecting those models to other parts of mathematics, like random matrix theory, representation theory, those kinds of things. So we will focus on two specific examples of these exactly solvable models. One is exponential last passage percolation, where the underlying noise space is IID exponential random variables on Z2. And the second one can think of it as a limiting semi-discrete limit of the discrete last passage percolation, where the noise space will consist of a sequence of independent two-sided Brownian motions. Okay, so for the first talk, for my talk, I will mostly be restricting myself to this exponential LPP setting, but the Brownian last passage percolation would be important for Shushendru's talk. Okay, so let's define things more concretely. For exponential last passage percolation on Z2, so as I said, we are putting IID weights, standard exponentials on each vertex of Z2. Now, for any path, so this diagonal direction is the time direction, and the anti-diagonal direction is the space direction. So we're looking at upright paths that are moving forward in time. And for every path, the weight of the path is just sum of the x variables along those paths. And for any 2 points u and v, we define the last passage percolation, last passage time from u to v to be the maximum over all paths pi connecting u and v, the weight of the path pi. Because exponential variables are continuous, almost surely there is a unique geodesic between every pair of points, and we will sometimes denote that geodesic by gamma. Okay, so as I said, this is an exactly solvable model. So a lot is known about, so this model actually is one of the models for which the KPZ predictions have been rigorously verified. So what is known? So the earlier results go back to early 1980s due to Rost, where it was shown that, so if you look at the last passage time starting from the origin to the point nx, ny, then the growth is linear in n. So if you scale by n, it converges to the constant square root x plus square root y whole square. So you have this sort of a shape. Okay, so in particular, if x equal to y equal to 1, you get this limit constant 4. And this is the exponent 1. So exponent 1 gives you the first order behavior of growth, which is linear. Okay, so the exponent 1/3 is the fluctuation for this quantity. So let's only focus on the 1, 1 direction, but there are similar results in other directions as well. So if you center the last passage time from from the origin to n comma n by the typical value 4n and scale by a constant times n to the 1/3, then this weakly converges to some non-degenerate random variable, which happens to be the GUE tracy-Widom random variable, which is a familiar universal scaling limit from random matrix theory. So that's the exponent 1/3. And the exponent 2/3 governs the decay of correlations in the spatial direction. So for example, it will show up. So if you look at the geodesic joining the origin and the point n comma n, the typical distance of the geodesic from the straight line joining the two points would be of the order n to the 2/3. So that is where the 2/3 exponent shows up. Okay, so these are some of the basic one-point information about this exactly solvable model of last passage percolation, the exponential last passage percolation. Okay, so this is the one-point information, but you can ask a more complicated question, right? So you can ask, what happens if you look at collection of pairs of points and look at the joint distribution of the last passage times? Okay, so here the conjecture is that under a certain scaling of space-time, you should get a non-trivial limiting object. So what is that scaling? So you should scale this time direction by n and the space direction by n to the 2/3. That means, so if you look at a point, say this point, which is s times n away from 0 in time direction and x times n to the 2/3 away from 0 in space direction. Now there are some constants which I have written down here, but I won't talk about those. So that point maps to x comma s. So in particular, this n by n to the 2/3 rectangle maps to a unit square. Okay, so if n is sufficiently large, so given any 2 points x comma s and y comma t, where s is less than t, you can take n sufficiently large so that the last passage time between x comma s and y comma t, they're well defined if n is sufficiently large. Right? So now you define your field, a 4-parameter field indexed by this initial space-time point and the final space-time point. So you define the 4-parameter random field by considering the last passage time from x comma s to y comma t. Now you go back in the pre-limiting model, and you center it by its typical value. So that would be 4 times t minus s times n, and you scale by some constant times n to the 1/3. Good. So this is a 4-parameter field indexed by n. So now what is expected is that as n goes to infinity, you should see a universal random object in the weak limit, which is a random field, again indexed by these 4 parameters. So this was constructed at the about 2 years back by this work of Dauvergne, Oatman, and Vera, where they constructed this limiting object, which they call the directed landscape, starting from the different model of Brownian last passage percolation, not the exponential last passage percolation. But I mean, it is expected that the same thing should hold for exponential last passage percolation and other models. It might even be known, but I'm not sure if it's written up anywhere. So for this talk, maybe just treat this as a conjectural picture. Okay. So, but even though the full joint distribution might not be still rigorously known for the exponential LPP, a lot is already known. So in particular, if you fix the starting space point and the starting time point to be 0 and the finishing time point to be 1, and only vary this finishing space point. So now you have a 1 parameter field. So that is known to converge to a stochastic process called AD2 process minus a parabola. Okay, so and as you can see that the underlying model has lots of invariance and scaling properties, right? So in particular, you don't have to start from 0 and end at x, right? You can start from any fixed point a and end at x plus a. You still get by translation invariance the same AD2 process. So instead of going to time 1, you could go to time t and change your scaling accordingly. You should still get an AD2 process. So lots of AD2 processes in this occur as this limit of as functionals of this conjectural limit object. Okay, so I'll not say that much about an AD2 process, but let me just say that it's a stationary process. Okay, so not right now. I'll have occasion to come back to it later. But let me, for now, just say that AD2 processes is a stationary process for which the 1-point marginal is given by the GUE traceability distribution. Of course, because if you set x equal to 0 here, you get AD2 at 0, and I have already said that the weak limit is GUE traceability. Explicit formulas for multi-point distributions are also available. But those are complicated formulas involving freedom determinants and extended Airy kernels. So this is something we won't really go into. So the convergence to Airy process in terms of finite dimensional distribution was shown by Borodin and Ferrari in 2008. And one can use tightness to upgrade this to weak convergence. Okay, so the general program for this talk and the next would be to understand the geometry of this conjectural limit object, the directed landscape, and also of its prelimits. Now, there are a lot of ways one can go about trying to understand the geometry of this object, but one particular way would be to understand. So as I said, there are many different AD2 processes coupled across space and time, right? So one particular way would be to understand this coupling structure of these AD2 processes. So what we'll do in these two talks is we'll investigate two very basic questions along these lines. So in my talk, we'll consider AD processes coupled across time, and in Shishendu's talk, he will talk about AD processes coupled across the spatial direction. Okay, so that was the rundown of what we plan to do in these talks. So maybe it's a good time to pause and see if there are any questions.
So maybe I have a quick question.
Yes.
So this how does this AD2 process look like? I mean, it's a measure, it's a distribution. It looks a little bit like a white noise.
So it looks locally like a Brownian motion. That's pretty much, it's a stationary process, but locally it's like a Brownian motion. Okay. So that is what we will use for the most part. So there are complicated formulas. You can ask. So there are things known about how the correlation decays and things like that. But for most purposes, when we want to understand the geometry of last passage percolation, some version of comparison between Airy process and Brownian motion is what turns out to be the most useful. Okay, so right. So maybe let's move on. Right. So what are the questions that we are investigating? So we are investigating correlations in time, right? So I fix the initial point to be 0, 0, and I vary the final point in time. So let's say I'm looking at the final point to be 0 tau. Now, as tau varies, this is a stationary process, or in the limit it would be a stationary process. Not the prelimit is not necessarily stationary, but so we want to understand the autocorrelation function of this process, right? So we want to understand this quantity rho n tau, which is the correlation between this function wn from 0 to 0 with the function wn from 0 to 0 tau. And we want to understand. So of course, maybe it's a bit too much to to ask to understand this for explicitly for all tau, although that can be done for certain special settings. But what we will be particularly interested in is to understand the short and large scale asymptotics. So in particular, we want to understand how this correlation behaves as tau goes to 0 and tau goes to 1. Okay, so for this talk, I will prefer to work with the unscaled object, so the last passage times directly. So we will work with just the covariance between, for the passage time from 0 to n, well, the origin to n comma n, I will just shorthand it as saying 0 to n, and the passage time from 0 to r. So r is, you should think of r is like tau times n, but for some of the results, we won't need r over n to be fixed. Okay, so we would just try to understand this limit when r and n are both going to infinity, and when r over n is small, and also when r over n is close to 1. So I should mention one thing is that there are exact formula for these two-time distributions, explicit formula, which there were some physics replica calculation by Ledusal and co-authors a few years ago, but there are rigorous results by Johansson, and then Johansson with Mustazi Rahman, and then there are these papers by Jinho Baik and Zipeng Liu, and also by Zipeng Liu, where in different settings, like different models of last passage percolation or TASEP, they worked out the explicit formula for the two-time distribution for last passage percolation or something related. But what appears to be the case is that these are very powerful formula, but also very complicated. So extracting asymptotics for the covariance from these formula, although in principle should be possible, it does not appear very straightforward. Okay, so before I move further, let me also introduce another bit of generality. So far, we haven't said anything about the initial condition. So we have just started the model from time 0, but we can also put an initial condition at time 0. So how does one do that in the last passage percolation, in the discrete lattice setting? So the natural way to do it is, so remember time 0 in our case means the line x plus y equal to 0. Okay, so what we would do is that we would add a function pi on this line. So just because by translation invariance, we just set pi of 0 to be 0. And then how do we calculate the last passage time there? So what we will do is that, suppose we want to calculate last passage time with this initial condition to some point v. So what we'll do is that we'll check every point u on this line. We'll calculate the usual last passage time from u to v. And then we will add the initial value pi of u to that. Finally, we will maximize over all u. So that would give the last passage time starting from this initial condition pi. Okay, so the more, you can ask more generally, what happens to the covariance between this last passage time to n and last passage time to r, starting with some specific initial conditions. Okay, so in this business, most of you would know that there are 3 initial conditions which are considered somewhat special. So the first initial condition, which we'll consider, is the wedge or the droplet initial condition. And so this is, we set the value of pi to be 0. Well, this should really be bold 0. So this is the origin. At 0 to be, at the origin to be equal to 0 and minus infinity everywhere. Now what that ensures is that, you never hit any other point, because if you are at any other point on that line, you will have a penalty of minus infinity. So that means you are actually considering the point-to-point passage time from the origin. So this precisely corresponds to the case I have already introduced. The second initial condition that we'll be considering is the flat initial condition, which is just that pi is identically equal to 0. So this is just the point-to-line last passage percolation. So here the passage time to n is just the maximum passage time from n to the line x plus y equal to 0. So here, so this is also an exactly solvable model. So here, instead of the GOE Tracy-Widom distribution, you get the GOE Tracy-Widom distribution. And instead of the AD2 process, you get the AD1 process. But again, there are formulas available. And the third initial condition, which I mentioned briefly, but I'll not really talk about in this talk much, is the stationary initial condition. And there, your pi is just a two-sided random walk with IID increments. And the increments are, difference of exponential random variables, and this rho corresponds to the density of the task set from which you get this initial conditions. So I'll not really talk much about the stationary initial condition, but this is also another important initial condition. So what were the conjectures? So about this. So the first sort of mathematically precisely formulated conjectures that were published, I think, was this work of Ferrari and Spahn. Although there were some other people also working on this. I will mention some of it later. So this is in this work in 2016. They considered, so they look at this r equal to tau n. So fix r over n equal to tau and then send n going to infinity. So they did not prove that this limit exists, but it has been proved subsequently. But they considered this limit, and based on partly rigorous heuristics, they conjectured an exact formula for the stationary initial condition and exponents governing the asymptotics for tau going to 0 and tau going to 1 for both the droplet and flat initial condition. So there was some earlier numerical evidence of this in the physics literature. But this, as far as I know, is probably the first mathematically precise formulation that was published. And over the last few years, these conjectures have now been made rigorous in our works and other works that I will mention subsequently. So first, let me state our results for the droplet initial condition. So this is a work with Shishendu from a couple of years ago. So what we say is that there exist universal constants such that for all n and r sufficiently large, these scaled covariances are like a constant, upper and lower bounded by different constants times r over n to the 2/3. So of course, you expect if r is much, much smaller than n, the covariance should be small. It should decay to 0 when you scale it by n to the 2/3. And it says that it decays to 0 in this exponent r over n to the 2/3. So that is the tau going to 0 asymptotic. So r over n is like tau if you prefer to think of it that way. Now the other direction, I have stated the results in terms of correlation because it looks slightly neater, because there the covariance should actually be very close to the variance because r and n are very close. So the correlation actually is very close to 1. And so what we had shown is that, so 1 minus the correlation, again, goes to 0 as 1 minus r over n. This now is small. This is like 1 minus tau as tau going to 1. power 2/3. So there's 2/3 exponent occurring in both the cases. Okay, so this is the result for the droplet initial condition. Now, there were parallel results. So simultaneously, as we finished this work, there was this paper by Ferrari and Uccelli, initial condition, but their setting was, again, the Ferrari response setting. So they set R equal to tau n and n goes to infinity limit. They actually showed that the limit exists. And not only that, they also obtained, so we have this estimates up to constants. They had the precise value of the constant up to the smaller order errors, but their result was in the limit. And their work, they had also proved the exact formula that was conjectured for the stationary initial condition. And what they showed further is that if you look at the tau going to 1 asymptotics, the exponents are same for all the 3 initial conditions. Okay, so this was all Ferrari and Uccelli. And then there's this work by Corwin, Ghoshal, and Hammond from last year, where they had proved an analogous result for time correlation for the KPZ equation. So I should mention that I first learned of this problem from Alan Hammond in 2015. So when he and Ivan were thinking about this, but in the Brownian setup or in the limit. So they never published their work, but subsequently they had this result in the positive temperature setup for the KPZ equation. Right. So that was the story about the droplet initial condition. So remember, after this work of Ferrari and Uccelli, what was left is that so the tau going to 1 asymptotics had been covered for all the 3 initial conditions. Tau going to 0 asymptotics has been covered for the droplet and the stationary initial condition. What was left was the tau going to 0 asymptotics for the flat initial condition. And it's interesting because there you actually see a different exponent. So for flat, in the tau going to 1 asymptotics, there is universality in different initial conditions, but in the tau going to 0 limit, you see different exponents. So the stationary and the droplet initial conditions give the same exponent, although for different reasons. But for flat initial condition, you actually see a different exponent, and this is what we had shown in this work from last year with Shishendu and Lingfu Zhang, who's a PhD student in Princeton, for those of you who don't know him. So what was our result? So again, here we actually consider the limiting regime. So we showed that quantity, the limit of scaled covariance, is of the order of tau to the 4/3 up to a constant in the lower bound, but for the upper bound we had a subpolynomial factor. So it's like upper bound is a constant times tau to the 4/3 plus tau to the 4/3 plus the law of 1. Okay, so a few remarks are in order about this result. So as I already pointed out, this is for the limit. Although we can prove some version of this result in the pre-limit, but there, depending on how small R over n is, you'll need to take n sufficiently large, and this is because we are importing some estimates from the limiting Airy process and its functions. So that is one, and see this subpolynomial factor. So we believe that subpolynomial factor should not be there. It's an artifact of the proof. I will talk about it a little bit later. But that the lower bound should be the right one. The upper bound should also not have that subpolynomial factor. And one other thing that I wanted to mention is that the result is fairly robust in the initial condition. So you don't need the exactly solvable flat initial condition. You get the same exponent as long as the initial condition is not growing too fast. So if it is growing sufficiently slowly, like a small exponent smaller than half, you should get the same correlation behavior. Okay, so I have about 15 minutes. Hello? So how much time do you have?
You could go up to 25 more minutes if you wanted.
Right, so about 15, 20 minutes. Okay, so in the time that I have remaining, let me try to tell you a little bit about the basic ideas that that go into the proof. So yeah, so let me just start with the heuristics for the droplet initial condition. So for the droplet initial condition, the two asymptotics are much less than n, and n minus r much less than n. Those are not very difficult, not very different. So we will only discuss one of those cases. The other cases are sort of quite similar. So why? So translated in this language. So what we want to show that the covariance between these T0n and T0r is of the order of r to the 2/3. That's what we want to show, right? Because so remember that. Let me just go back. Yeah. So after scaling by n to the 2/3, we had this r over n to the 2/3. So the covariance itself is of the order of r to the 2/3. That's what we want to show. Okay, so let's look at this picture. So x is the weight from 0, 0 to r comma r, and the other thing, let's the geodesic from 0 to n be this red and blue path. So the total weight is z plus w. So what we're interested in is the covariance of x and z plus w. Now, this quantity w, because of the randomness of the point where it intersects this line x plus y equal to r, this is not quite independent of x, but you believe that this weight should not really have much correlation with this weight. So what you believe is that the correlation order should be same as the covariance order should be same as the covariance between x and z. And that again, should be of the same order of the variance of x itself, which is r to the 2/3. So this is the last passage time from 0 to r, so the variance is of the order of r to the 2/3. So so how do we make it rigorous? So for the upper bound, what we show essentially is that if you look at this, if you say y to be the passage time from rr to nn, then what we would show is that x plus y is a good proxy for z plus w. So z plus w is the quantity we want, but we'll show that x plus y is a good proxy of that, and that helps us because if you look at covariance of x and x plus y, because x and y are literally independent, so you will get just a variance of x. So what do I mean that x plus y is a good proxy for z plus w? It's exactly in this L2 sense. So we want to show that variance of x minus z and variance of y minus w, or rather second moment 7, are of the order of r to the 2/3. So I won't show you the calculation, but it should not, it takes like 5 minutes of thinking to understand why this quantity, why these two estimates. You can use Cauchy-Schwarz once you have these two estimates to show that covariance of x and z plus w should be well approximated in the upper bound by covariance of x and x plus y. Okay, so that's the idea, but how do we actually do it technically? So the key observation is that this point V, which is the intersection of the geodesic from 0 to n with the line x plus y equal to r, it cannot be too far from the point r. So actually, typically, this point will only be r to the 2/3 away from this point r. Now, I have already mentioned this transversal fluctuation of the geodesic as a whole to be n to the 2/3, but there exists a local version of the same result, which we did in an earlier paper with Shodav Sarkar and Alan Sly, where we showed that if you are at distance r, from one of the endpoints, the transversal fluctuation of the geodesic is of the order of r to the 2/3, which exactly means that this point V should be order r to the 2/3 distance away from the point R. Now, once you have that, we're in good shape because, so look at these profiles from 0, 0 to this line and from n to this line. So these are A2 processes, right? Up to the subtraction of a parabola. And as I already mentioned, A2 processes look like a Brownian motion. So it means, well, I mean, after a fashion, one can make all these things rigorous, but at a heuristic level, that should tell you that the fluctuation of these profiles should be diffusive. So once you are at a distance r to the 2/3, you should not fluctuate by more than r to the 1/3. But y minus w and z minus x, these are precisely the fluctuation of these profiles. So typically, x minus z and y minus w, this should be of the order r to the 1/3, which gives us the L2 estimates that we want. Okay, so that's how the upper bound is made rigorous. Now, for the lower bound, it's a bit trickier because we cannot directly use Cauchy-Schwarz because we have to rule out cancellations, right? So the main idea here is to use the FKG inequality. So how is the FKG inequality applied in this setting? So observe the following, that passage time between any two vertex is an increasing function of the configuration of weights. What does that mean? It means that if we increase the weight of any one of the vertices, the passage time between any two vertices can only go up, it can never go down, right? So these are increasing functions. So what does the FKG inequality say? The FKG inequality says that any two increasing functions are positively correlated. In particular, the passage time from 0 to r and the passage time from 0 to n, they are positively correlated. Okay, so to get a lower bound on the covariance, it suffices to only consider a positive probability event such that if we can show conditional on that event, I have a lower bound on the covariance. So that part will give me a lower bound, and the FKG inequality will say that the contribution from the other part is non-negative anyway. So essentially, we will be done if we could create a positive probability event on which these paths attaining x and z, they will be roughly the same. In particular, I mean, they will spend a lot of time together because that should give you a positive correlation, a uniformly bounded error from zero correlation. Okay, so how is that done? It's done in the most natural way imaginable. So what do? We want the paths to be close, right? So what we do is that we try to force an environment so that the paths cannot wander off too far. So what we do, we take a small strip around this line joining 0 and r, and around that strip, this deep blue region, this is what we call a barrier, which means crossing this deep blue region will be penalized a lot. So that would disincentivize the paths to actually pass through this blue region and the deep blue regions. Okay, and one can show that this can be done with positive probability. And once you have done that, so conditional on this barrier event, now you expect that the conditional covariance between x and z, which means this purple path and this purple plus this whatever yellow bit below the line x plus y equal to 2r, the conditional covariance should roughly be same as the variance of the last passage time from 0 to r, which is constrained. So instead of looking at the last passage time obtained by maximizing over all paths, we'll maximize only over paths that never go outside the strip. There will be some error which comes from the contribution of the unlikely events where these paths actually do go through these barriers for some weird reason. but up to the error, you expect this to be the conditional covariance. Now, how do we make sure these errors are negligible? So it's actually not very hard to show that the variance of this constrained passage times, it's of the scale r to the 2/3, but it's an increasing function of theta. It grows like theta to the -1/2. Now that's natural, right? Because if the width of the strip was 1, then there's a single path and you'll have a fluctuation of order square root n rather than n to the 1/3. So the variance increases if you make the strip narrower. And by making the strip narrower, by choosing theta sufficiently small, we can drive up this variance so that the error terms actually become negligible. Okay, so this is how technically, we show that conditional on this barrier event, the covariance conditionally is uniformly positive. Okay, so let me spend the last few minutes of my talk talking about the flat initial data. So recall the setup. We have R is some tau times n. Now, again, the basic input is always to understand the geometry of the geodesic. So if you look at the geodesic from n to the line x plus y equal to 0, now typically the endpoint of the geodesic is at a distance n to the 2/3 from the origin. Now, again, the transversal fluctuation, standard transversal fluctuation estimates. So that also tells you that if r is much smaller than n, the point where it intersects the line x plus y equal to r, that should also be typically at a distance n to the 2/3 from this point r. So now, if r is much smaller than n, the transversal fluctuation of this bit of the geodesic and this bit of the geodesic should ensure that these paths never get to interact. So this event, the typical event, should really not contribute to the covariance. Okay, so that's the typical scenario. But what does contribute to the covariance? What does contribute to the covariance is the unlikely scenario where the geodesic from n actually passes very close to this point r. So on the event that the point u0 lands within distance of the order r to the 2/3 distance of r, the geodesics with positive probability should coalesce and spend a positive fraction of the rest of their journey together. So this event should actually, again, as before, contribute an order r to the 2/3 to the covariance. And the probability of that event, so remember this u0 heuristically is like a uniform, it's like uniformly distributed on an interval of n to the 2/3. So what is the probability that it lands on an interval of r to the 2/3? It's like r over n to the 2/3, is tau to the 2/3. So if you combine that, on that probability tau to the 2/3 event, you have a contribution of covariance which is of the order of tau to the 2/3 times n to the 2/3. So combined, you get tau to the 4/3 times n to the 2/3, which is the predicted value that we prove. But how do we make this rigorous? So the lower bound, the basic idea is, again, as in the droplet initial condition. So we construct barriers and all. But now one needs to be a bit more careful because we need to control in a better way what happens, So we want to make sure that this u0 point lands close to this point r. And we also want to make sure that there is sufficient decay around this u0. So the profile from n to this line, it does not have too many near maxima. So these kinds of things one can ensure by some sort of abstract estimates about AD2 processes. In particular, we use translation invariance, mixing, and Brownian absolute continuity of the AD2 process, which together with the general theme of construction of barrier events that was already done in the droplet initial condition gives a lower bound. The upper bound is a more interesting thing here. So remember, we want to So for the upper bound, what we want to show really is that this point u0 being very far from the point R should not contribute to the covariance. But the problem, one obvious problem with that is that u0 depends on the whole space. No, but we want to preserve as much independence as possible. So what we do is that we show that Umax is a good proxy for U0, where Umax is the maxima of the profile from n comma n to this line x plus y equal to 2r. In particular, Umax is actually completely independent of whatever happens below that line. So what we will show is that Umax, if the distance of Umax to R is much larger than R to the 2/3, then it does not contribute substantially to the variance. Okay, so what we do essentially is that we fix where the location of Umax is in some interval, and then we sum over all possible interval, and we show that the contribution is summable and at the right scale. But why is that true? So here we use this local Brownian property of the AD process. So because it's locally Brownian, so really what the process around Umax should look like, it's a Brownian motion condition to stay below 0. Okay, and so there is diffusive decay of such processes. So as soon as the distance of Umax from R is larger than R to the 1/3, typically the shortfall of the profile here compared to what the value of it is at Umax should be much larger than R to the 1/3, which is something that the fluctuation of this path cannot make up. Which means that if Umax is far enough away, the global geodesic should not make this jump and join with this one. It should stay far away and should not interact with the other geodesic. So the contribution of this part should be small as we had heuristically suggested. So now, but how do we do this calculation? So the basic idea is to do all those calculations. We want to understand how unlikely it is that given that Umax is far enough away, that the profile here is sufficiently competitive. So we do those calculations for a Brownian motion, and then we transfer it to the actual profile, which is like a 2 process minus a parabola, by using strong Brownian comparison estimates. Okay, so I'll maybe say a little bit about that in the next couple of slides. So, but this is how the proof is completed. Okay, so in the last couple of slides, let me just say what are the inputs. What kind of integrable inputs did we use? So the key estimates were the 1-point moderate deviations. So the last passage time minus its typical value at the standard deviation scales. So there are many such estimates available if you do not want the optimal exponents, but I prefer these results by Ledoux and Ryder, where they obtained the optimal exponents with a rather soft arguments using the correspondence to Laguerre unitary ensemble and these tridiagonal representations for Laguerre and Hermite unitary ensembles. So these are the absolute key estimates. And these key estimates go into the geometric tools, some of which I have already mentioned, that include this local transversal fluctuation of geodesics or polymers, then coalescence of geodesics, and then the diffusive fluctuation upper bounds for the pre-limiting AE2 profile. So remember, for the droplet initial condition, we did not use any property of the AE2 process. So this diffusive fluctuation bounds were also proved directly in the pre-limit using these geometric techniques. But unfortunately, these were not enough for the flat initial data because we needed those strong Brownian comparison estimates. So there we use a very recent result by Jacob Calvert, Alan Hammond, and Milind Hegde, where they actually provide a strong control on the Radon-Nikodym derivative of AE2 process minus a parabola with respect to a Brownian motion of diffusivity 2. And this is precisely where this subpolynomial factor comes. So what they show is that if you have an event which has Brownian probability A, then the probability upper bound in the AE2 process is A times this exponential log 5 to the 6th 1 over A. Okay, so this is where that subpolynomial factor came in the upper bound of our flat initial condition. no, I mean, yeah. So this is a very technical result, and this hinges on the Brown the airline ensemble, which was developed by Ivan and Alan a few years ago, which is extremely useful for understanding either Brownian LPP or the limiting process you get from there, the directed landscape. So I will stop here, and Shishendu will tell you a lot more about this Brownian Gibbs property and its consequences in the next talk. So I'll stop here, and thank you for your attention.
Okay, thank you very much. So let me go here, and so I will prepare this. So now you can unmute yourself and give a round of applause for Reed if you're willing to. And so you can also do some. We have some time for questions. And so you can either write on the chat or talk.
So Rudy, so you get results for very general initial data, or how much does it rely on kind of being flattish?
Yes, so this is not written in the paper, but we sort of give a detailed outline of how to do this result for the general initial condition. So what we expect, so as soon as you have an initial data which grows with an exponent less than half. So if pi of s is like s to the half minus epsilon. So if mod of pi of s is less than s to the half minus epsilon for every epsilon, so you get the same exponent. So it is similar to, so there is this paper by Quastel and Rebenick, right? This how flat is flat, where they show a similar thing for the one-time distribution, that if your growth is less than a half exponent, then you still get the airy one-type behavior. So it's similar. So we never really use the convergence to GOU Tracevidum or airy one. So we are only using 1-point estimates, and then so that sort of lets us work with these more general initial condition, which as long as it's not too curved, all the heuristic that I presented, that these paths cannot really come, if your Umax is too far away, then it should not really jump back to the shortest geodesic. That sort of heuristic still works as long as your initial condition is not falling off too fast, which happens in the droplet initial condition for which you get a different exponent. So as soon as you have that, you get the same exponent. So that's yeah.
All right, thanks.
So if there are no more questions, maybe we can just thank again Rudy for his talk.
Yeah, thanks very much.
And so now,
Maybe we'll pause for a minute or two.
yeah.
Let's give Shishendu the co-hosting. I think Milton, you need to do that.
Did I do that?
Hi, Ivan.
Hey, Shishendu.
Hey.
How are you?
Good. How are you?
Good. So is this picture something you took, or this is like an official?
No, there are a bunch of available things. Yeah, I've been just using that. I actually tried to sort of mix things up. I use different things, different days. Yeah.
Mm-hmm. Oh, I see. Berkeley's even written on the upper left. So.
Yeah. I mean, it is a bunch of backgrounds that so that's a bit boring otherwise.
So what is it? It's 8 a.m. there?
Yeah. Yeah.
So Reedy's going to go to sleep and you just woke up.
Yeah.
All right. Do you want to share the slides?
Oh, yeah, sure. Do you mean share my screen or just email you the slides? Or?
Oh, no. Well, Sure.
I'll do that after my talk, maybe. Okay. Yeah, I can share my screen. Let's see. So should I be able to just share?
Or do you have two computers? Or
Yeah, let me just.
you should. You're co-host right now.
Okay, good.
Video.
All right. Mm-hmm.
So right now, there we go. Okay.
Okay.
All right, so we'll wait maybe one more minute in case people needed to use the restroom. So the smoke has cleared in Berkeley?
A little bit, yeah. Mm-hmm. But there were power outages throughout the. I'm like, I didn't luckily have anything bad happening, but some of the colleagues actually had internet and electricity out for like a day or more than that even, yeah.
Right, yeah, I saw that there were cycling outages.
Oh yeah. They're just sort of doing some general shutdowns to prevent damages, yeah.
Hey.
Yeah, everything's falling apart, yeah.
Yeah. Okay, maybe we'll get started. So it's a pleasure to have Shirshindu Ganguly speaking second of this double header, and he'll be speaking about fractal geometry and Brownian last passage percolation and the directed landscape.
Yeah, so thanks a lot, Ivan, and thanks a lot to the organizers for the invitation and everybody for showing up. So just to clarify, so I don't think should I be able to see the chat if there are questions?
I'll point out if anything.
Okay, cool. Thanks. Yeah. So thanks everybody for showing up. And so this is sort of a second part of this double talk, and it sort of broadly tries to address the same theme regarding sort of geometry of this space-time last passage model. And so as Riddhi was mentioning, he was focusing more on things as the time coordinates is allowed to vary, and the basic thing that you can look at are correlation behaviors. So the focus in this talk will mostly be when you vary things in the spatial direction. So as is probably already clear, so there are two directions. So one is space and one is time. And so we'll mostly try to vary things in space and try to see how things are coupled in sort of a joint distribution. And so again, with more focus on sort of some certain nice fractal behaviors that emerge. And the model in question will be slightly different because of some nice properties. And this part of the talk will be based on a couple of papers, one with Riddhi and Alan Hammond, and the second one with Eric Bates and Alan Hammond. And again, feel free to ask questions for the talk. You can stop me, you can unmute yourself. I think that's allowed, or you can write in the chat. Okay, so just to sort of get this framework started, so Riddhi already described a lattice last passage percolation model where you look at Z2 and every vortex has an IID weight attached to it. But here we will sort of focus on a more semi-discrete version of that. So where you can think of this as a sort of limiting model gotten from the discrete one. So here, instead of the lattice, I'll have, okay, so this is visible. All right. So you'll have like a bunch of lines. So think of the lattices as being sort of taken after passing to the limit. The lattice has become sort of straight line. So you have a bunch of copies of the real line indexed by Z, and for each line you have an independent two-sided Brownian motion. So this is the y-axis. These are independent copies of two-sided Brownian motions, which are all vanishing here. Okay, so that's our basic noise space, and clearly this is something that you can get from taking the limit of the discrete model. Okay, and okay, so again, so this is 0, 0, this is NN, and instead of looking at lattice paths, what we will look at are oriented paths. So how does an oriented path look like? So you start from 0, 0. So let's say we want to go from 0, 0 to NN. So what you do is you start from 0, 0, you stay on this line for a bit. So you say, let's say you go from 0, 0 to Z1, comma 0. Then you jump up. Then you spend some more time here. So Z1, comma 1. So look, see the x coordinates of these two things are exactly the same. So you literally just jump up. You spend some more time here, and then you continue till you get to where you want to go to. All right. And so for any such oriented path gamma, notice that there is no, unlike the lattice, there is no noise that you accumulate from here, right? So there is no vertical sort of noise here. So you only pick up noise on your horizontal journeys. So for any such path gamma, the energy of gamma will be exactly what you get if you integrate the white noise or the derivative of Brownian motion along the path, meaning you just pick up the Brownian increments. So this one gives you B's. So let's say the Brownian motions are denoted by B0, B1, blah, blah, blah. So then the first journey from 0, 0 to Z1, comma 0 just gives you a B0 of Z1, right? So that's literally the Brownian increment. And then subsequently you pick up the Brownian increments from the other level. So the second level gives you B1. So this is the Brownian motion, which is seeing the action. So B1 of Z2 minus B1 of Z1. So it's literally the discrete model, but adapted to this sort of semi-discrete setting. And then you add up all these increments, and that's going to be the energy of this particular path gamma. Okay. And let's sort of start with some notation that they might slightly differ from maybe what Riddhi was using, but basically they're denoting similar quantities. So let's say Mn, which is going to be the sort of shorthand for this slightly more elaborate object, which is maybe more evocative. So M00 to Nn denotes the weight between 0, 0 and Nn, which is exactly the maximum energy of any path gamma between 0, 0 and Nn. Okay, so for any oriented path, we just define what the energy is, and now look at all such possible paths. You look at the one which has, you look at the maximum energy among all of them, and we will call that M00 to Nn, or sometimes Mn. And as was already discussed, so this maximizing path goes by sort of various names. So mostly we will call it the geodesic. Right, so the framework is quite similar. And of course, obviously, you can define mxi to yj in a natural way. So take a point xi. Like, of course, this is well defined only when xi appears somewhere here and maybe yj appears somewhere here, so that you can so that you can actually get some oriented paths. You cannot have y smaller than x. Okay, so once you have xi, yj sort of satisfying this order constraint, then you can of course define mxi to yj similarly by looking at the maximum over all paths which go from xi to yj. Okay. Okay, so how do these quantities behave? So the law of large numbers is slightly different from the exponential setting from the last talk, but roughly the same. The precise constants are slightly different. So M00 to Nn, or Mn as we called it, the law of large numbers is 2n. And then the fluctuation is what is governed by this kp's exponent n to the 1/3. So the fluctuation term is of order n to the 1/3. And so whatever you get by dividing by n to the 1/3 is an order 1 quantity. So this Wn is an order 1 quantity. Oh, so I see some chats. Sorry.
No, I responded in the chat, so don't worry. I'll let you know if anything.
Okay. Yeah. So, and more generally, instead of if you sort of incorporate the KPZ scaling into the definitions of xn, I, and y and j. So let's look at two different heights, Sn and Tn. So S and T should be thought of as order 1 quantities between, let's say, 0 and 1. So n is sort of really the scale of the system. But instead of looking from level 0 to level n, let's look at some level Sn to level Tn. And then let's say the spatial locations are Sn plus some n to the 2/3 times x. So this is exactly what incorporates the KPZ scaling in the spatial direction, which says that roughly interesting things happen only when you look at things which are separated by n to the 2/3. So Sn is the time, which in this case was 0. And now you look at some spatial location, which is Sn plus some n to the 2/3 times x. So x is again an order 1 object. And similarly, you go to Tn, and the spatial location is Tn plus n to the 2/3 times y. Okay, so once you do that, then the behavior of this object is 2 times t minus Sn, because like here, where the time difference was of exactly, when the time difference was exactly n, here the time difference is t minus Sn, so that governs the law of large numbers behavior. There's also linear correction coming from the difference between y and x, so that's again this. And then the remaining thing is exactly what we saw. It's n to the 1/3, which is the fluctuation behavior times some order 1 quantity. Okay, so that's really how these quantities sort of behave. So the law of large numbers is dictated by this constant 2 and this temporal, how much advance you're making in the time coordinate. And also there is some linear correction depending on what the spatial points are. And then eventually, once you subtract these guys off, you're left with some n to the 1/3 order object, which is the fluctuation behavior. Okay, so of course, things are happening at time and spatial scale dependent on n. So if you want to study them in sort of a reasonably, in sort of a limiting sense, it would make sense to compress everything to an order 1 picture. And this is what we sort of do next. So like, remember, so this is, let's say, level 0, and this is level n. So let's say we go from the point, the constant 2 here is not super important. So let's say we go from a point which is at distance n to the 2/3 times x from the origin, and go to a point which is at distance n to the 2/3 y from the point nn. Okay, so roughly you want to make sort of a diagonal journey, but then you're sort of moving slightly away from the origin by distance n to the 2/3 times x, and then you're going to something which is away from nn by distance n to the 2/3 times y. You want to compress everything so that under the scaling will sort of look like a picture like this, where this distance n in the temporal direction gets scaled to a distance of order 1, exactly 1 actually. This n to the 2/3 x becomes an x, and this n plus n to the 2/3 y becomes just a y. Okay, so now you have taken a picture of scale n into an order 1 picture. And of course, this will also affect how your paths look like. So then oriented path in this picture look like something which was just taking some horizontal excursions and then going up and then again sort of spending some horizontal time. Under this scaling, they will look something slightly zigzaggy. So the horizontal pieces will look horizontal again, although much smaller. And then the vertical pieces will become slightly sloped. And then there's a precise gradient that you can write down. But it's not super important. The point is the paths go through some change. Okay, so we have taken a big sort of order n picture. And then the point of this slide is to see that there is a way to make it into an order 1 picture, which would be convenient to study. Any questions so far? Okay. So uniqueness of geodesics. So if I fix 2 points, then almost surely it turns out that the path which has the maximum weight is unique. And that just comes from a pretty simple resampling argument. You can resample the Brownian motions to argue that. Essentially, you can show that it's very, like with property 0, 2 paths will actually have the same weight where one of them is the largest. However, there are uncountably many points here, and similarly uncountably many points here. So it's not unsurprising if I tell you that there will be points which might violate this behavior and admit more than one geodesic. So fixing 2 points, almost surely something happens, but almost surely there might be exceptional points. Okay. So the thing you should keep in mind is, given 2 fixed points, the geodesic is with property 1 unique. Okay. So we sort of showed the order 1 picture where we took a scale n object and reduced it to an order 1 object. So this is what the picture looks like. So the x-axis has been scaled to this, and the height n-axis has been scaled to something which has height 1 now. And so and things are allowed to vary in the bottom axis and also on the top axis, where the temporal distance is always 1. Okay, so you have squeezed everything, right? So you have squeezed basically the height 0 and height n object to this, and you're allowing points to vary on both the lines. Okay, so let's define the scaled weight. So the scaled weight is exactly the fluctuation term that I sort of mentioned earlier. So you don't have to look too much into this. So this is the weight between the unscaled objects. Recall that this n to the 2/3 x is what exactly scales to x here. And this n to the 2/3 y is what scales to y here. So this was the unscaled weight. And then this was sort of the law of large numbers behavior, which we subtracted. There was also linear correction that we had to subtract. And then I said that after subtracting this, what remains is an n to the 1/3 object, which is the fluctuation behavior. So you scale by n to the 1/3. So n to the minus 1/3 is what is multiplied here. So this is an order 1 object. So this is a random variable which is tight. So that is what we call it to be the scaled weight between x and y. So x and y are just two real numbers at level 0 and level 1. And w and xy is going to be the scaled weight, which is gotten by this formula, which is just the unscaled weight subtracting of the law of large numbers behavior and dividing by the fluctuation term. Okay, but now x and y are allowed to freely vary. Of course, there is something that I'm overlooking here because there was some constraint, right? In the unscaled picture, not every 2 points actually had a well-defined weight between them because y could have been smaller than x, in which case things would stop making sense because you only look at oriented paths. But let's not worry about that, because as n grows to infinity, this thing will become well-defined for any x and y in a compact set. So you can think of, for purposes, you can restrict your attention to a compact set and take n to be very large, for which all of these things start becoming well-defined. Okay, so now this creates a scaled energy field. Everything is of size order 1 between points of the kind x0, which is downstairs, and y1, which is upstairs. So we have taken some very big scale n object and reduced to us an order 1 field indexed by points x0 and y1. But as I indicated, you can also vary the time coordinates. It's not necessary to just sort of focus your attention to height 0 and height 1. You could have also taken some intermediate height s and height t. So in that case, you would have gotten something which we would have denoted by wn xs yt. This would be a notation. So x is the first spatial coordinate, s is the first time coordinate, y is the second spatial coordinate, and t is the second time coordinate. So in this picture, wnxy is the shorthand for wnx0 y1, because our time coordinates are fixed to be 0 and 1, and x and y are the things that are allowed to vary. Okay, but the more general notation allows for different temporal coordinates. Any questions about sort of the framework? So we have scaled everything, and so we get some order 1 random field, which is going to be the object of our study. Okay, so how does wn0y look? So recall wn0y was the shorthand for 00y1. So we are looking at this point 0, 0 at height 0, and y is allowed to vary at height 1. So as has already been mentioned to some degree, so this weight profile as y is, so you can plot this function as a function of y. So this weight profile actually looks like a parabola, just because of, and so this is sort of a general phenomenon. If you look at any last passage model, there is some super additivity implicitly involved, and that tells you that the shape theorem, the sort of the limiting shape has some concavity properties, and this is really the consequence of that. So the limit shape is a parabola, but then you have some fluctuations on top of that, which is exactly this thing called the Airy-2 process, which locally looks like a Brownian motion. So this function wn0y as a function of y looks like a parabola with some perturbation, and the perturbation is given by a stationary process, which is Airy-2. And again, a similar picture is true if 1 was replaced by any other time t. Okay, so that's roughly what this function looks like. Okay, so this scaled field, order 1 random field actually sort of satisfies some scale invariance in the exact scale invariance in the limit. So we don't want to go too much into that because it's not super important, but just to sort of state it. So recall that this 4 coordinates, this is the first spatial coordinate, second spatial coordinate, first temporal coordinate, second temporal coordinate. So if the temporal coordinates are s and t, then if you scale space by t minus s to the 2/3, like the temporal distance to the 2/3, and then divide the weight by the temporal distance to the 1/3, you essentially lose the effect of the time. So this thing, which looks at weights between times s and t, is in distribution similar to this thing, which looks at weights at this times 0 and 1. So you can go from the weight profile at height s and at height t, between height s and height t, and scale it appropriately using Kp's exponents to get to height 0 and height 1. So it sort of just suffices for our purpose to just sort of restrict to this. And again, this is sort of an equality in distribution, almost like it's an approximate equality because there is still an n here. but this fields Wn actually converge to some limiting object where this equality is exact. So this exact equality actually does hold in the limit. And so this is what the limiting object is. So this is the directed landscape, which was constructed by Dalvan, Ottman, and Virag a couple years back. So it's a random continuous function, W, from R upper arrow 4, which is a set of all 4 tuples where S is less than T. So again, like the space of all points where we think of defining a weight. So it's a random continuous function going from R4 upper arrow to R, such that it satisfies a few nice properties. One of them is, if you look at, so think of this, look at this picture. So this is height S, this is height T. So if you look at some intermediate height R, then the weight between XS and YT would be the maximum weight between XS and XS and ZR for some Z on this point. And so, right, so we want to look at the best passage time between XS and YT. So which basically means that there is a path which goes from XS to YT. So that path must intersect this intermediate height R at some point, let's say this point. So the best passage time from XS to YT would be the passage time from XS to this point, and the passage time plus the passage time from this point to this point. And this is exactly what is encoded here. So that's one property, which is exactly what you would expect, because this is the last passage. This is a scaling limit of a last passage random field. And this is exactly the super additivity type property that I was alluding to. And then also the different parts of the noise space are independent. So whatever happens here is independent of whatever happens here. And they all have the same law modulo some scaling. And the scaling is exactly what I sort of talked about in the previous slide. So no matter what your time coordinates are, you can always scale things back to make your time coordinates 0 and 1. So that means after scaling, everything has the same law. And what this property says is that the law coming from different parts of the space are independent. Okay, again, it's not very important. What it says is that there is a random field, which this last passage weight random field that we got by scaling things converges to. And so this is basically what the theorem is, so that there is a coupling of Brownian LPP and this random field such that the scaled field that you got from Brownian LPP converges to this random field. And so this is an error term. So it says Wn, when the system size was n in the Brownian LPP setting, after scaling is close to this random field W plus an error term. And the error term has some they have a very uniform control on this error term on compact sets. Okay, so this is the convergence result that they proved, which is a breakthrough result. It's expected to hold in other LPP models, but currently the precise proof is only known in this Brownian LPP setting. Okay, so that's the sort of limiting random field that I was mentioning, and this is exactly what is known as the directed landscape. Okay, so you have a random field of weights, and you can talk about geodesics in the directed landscape. So I see a chat. So yeah, so I'm not quite sure about the precise details, but I think it's sort of reasonably explicit in the sense that the way they construct the field is by a very explicit coupling to Brownian LPP. That's vaguely what I remember. I'm not completely sure about this. Yeah. Yeah, I think it's reasonably explicit because they have a good control on the error term. Okay. So now I will talk about geodesics in this limiting object instead of talking about geodesics in Brownian LPP. So take any continuous function, let's say between points XS and YT. So like Brownian LPP, we have to assign some energy to such a path. And there is a way to naturally assign energy to any such continuous function gamma by taking some finer and finer partitions. So take any path gamma, take some sort of mesh points on this path, and then look at the, so W was your directed landscape. So you can look at the W value between this point and this point, this point and this point, and this point and this point. So you can add these guys up. And now this thing will become smaller and smaller as you make the partition finer and finer. So the energy of this path gamma in the random field W would be sort of the limiting value of this sum of the weights along points in a partition as you make the partition finer. Okay, so there is a natural way to define that. And existence of geodesics and other measurability issues, where I mean, these are actually not completely trivial, the measurability issues of geodesics and other related properties, but they were actually addressed in this paper of Duncan, Dovon, Ortman, and Virag in 18, and later in our paper with Eric Bates and Alan Hammond. So there are some measurability issues to be addressed, but I won't go too much into that. Okay, so but the upshot is there is this random field, which is a limiting object. There is a way to make sense of geodesics in that object, and you can talk about existence and uniqueness of geodesics in that limiting object without talking about Brownian LPP anymore. Okay, so like we saw, so for any fixed S and T, the weight profile WXS, comma, when you allow to vary this coordinate, so fix the time coordinates S and T, fix one of the points to be X, and vary the other spatial coordinate. We know it's a parabola plus an area 2 type process up to some scaling. But what happens when you vary X as well? So for every X, you have this copy of an area 2 process with adjusted by a parabola. And now you can vary X, and so that gives you a joint coupling. Oh, so there's one more chat. Yeah, they do. I'm like, so I'll mention that. Yeah, they do under some conditions. So they will. So geodesics in the pre-limiting model will converge to the geodesic in the limiting model, provided that there is a unique geodesic. So that's really the sort of heart of this talk. I'll get into that later. Yeah. But the point is, you have all these area 2 processes centered at different points X. And so what happens when you vary them? What's their coupling structure? What's their joint distribution? So this is roughly the question that we're trying to answer. So fix, let's say for the rest of the talk, mostly we'll fix our time coordinates to be 0 and 1. Let's just take two basic X coordinates, -1 and 1. So you have the weight profile centered at this point is roughly a parabola centered here, plus some area 2 perturbation. Again, there is a parabola centered at 1 with some area 2 perturbation. And so now, but they're jointly coupled through this directed landscape. And we want to understand their coupling structure. Okay. Sorry. Oops. Yeah. So it turns out that sort of understanding how geodesics behave is actually the key to understanding this coupling structure. Okay, so let's see how you would imagine geodesics should typically behave. So take some point, take some maybe tiny interval upstairs at height 1. So typically what will happen is that, and look at geodesics which go from points in this interval to points -1 and 1 downstairs. So geodesics are trying to maximize their weight, right? Now, what will happen typically is that there will be some fertile region in the noise space, and all my geodesics will try to pass through that region, which means that geodesics actually, irrespective of what the destination is, should roughly pass through a common region, which would mean that they should meet. So geodesics typically coalesce. So if you take some typical interval upstairs, geodesics from any point upstairs going to either of the points -1 and 1 would typically pass through a common region, and so they would meet. That's roughly what the typical picture is. Okay, let's see what the consequence of this is. Okay, so let's look at the weight. So recall, so fix some point Y upstairs. So recall W10Y1 is this weight of the path, weight of the geodesic from 1 to Y. And let's look at the difference. So we want to understand the coupling structure. Let's start by looking at the difference, and we will see why it's a natural thing to look at. So we look at the difference of the weights, 2Y starting from 1 and -1. Okay, so the weight from 1 to Y is exactly the weight of the geodesic from 1 to Y. And similarly, the weight from -1 to Y is the weight of the geodesic from -1 to Y. And let's pretend that they meet. So there is some coalescence happening. Okay, so what is the weight? So there is some initial bit. So the weight geodesic from -1 to Y. And so let's say this is the meeting point. So there is some initial bit. Let's call the weight of the initial bit as I-1 when the geodesic starts from -1. And I1, oops, sorry, something is happening. Okay, yeah. Yeah. And let's call it I1 when it starts from 1. And then there is a final bit which is shared by both the geodesics, and let's call the weight of the final bit as Fy. Okay, final Y. So this weight from 1 is the initial bit, I1, plus the final bit, Fy. And this weight is again the initial bit, I minus 1, plus the final bit, Fy. So now if you take the difference, you see that the Fy sort of occurs in both the terms and they cancel out. And you're left with this term I1 minus I minus 1. And that's irrespective of what y was. As long as you see this picture, in every point in this interval, the difference is exactly going to be this. So which means that this profile, difference profile z, which is the difference of the weights starting from -1 and 1, is typically constant on intervals. Okay, so any questions about this slide where the geodesic coalescence directly implies something surprising maybe about the difference of the two weights? Okay, let's continue. Again, so let's go back to this difference profile. This constants are not super important. I'm like, so you know that there is this parabolas, and then there's some area on top of that. So if you look at the expected difference profile, so these are stationary processes which are order 1, right? So these will not really matter too much in the expectation. So the expectation of the difference profile is roughly going to be dominated by the expectation by the difference of the two parabolas. So you have a parabola centered at 1, you have a parabola centered at -1. So if you take the difference, it's actually going to be like a linear function. If you take two parabolas centered at two different points and take the difference, that's a linear function. And then on top of that, you have some perturbation. So the expected difference profile has linear growth. However, like we saw in the previous slide, typically coalescence happens, which means that this function, which is on an average growing linearly, is typically flat. Okay, does that make sense? Yeah, so feel free to let me know if there are questions. So this is sort of the important part of the talk where we see that something that is expected to grow linearly is actually quite often very flat. And so this is the graph, actually, this is a simulation of the difference profile. And see, as we sort of saw, it's actually typically flat, but it's also sort of, the picture indicates it's also monotone, which is maybe not very obvious. So this difference profile, if you, let me just go back to the previous slide just to sort of refresh our memory. So we know that the expected difference profile grows linearly. So we do expect things to grow monotonically on average, but it turns out that this is a random instance of that. And it turns out that in this random instance, it's also monotone, not on average. Okay, so let's actually, but this turns out to be a deterministic fact. So and it's actually a short proof. So we'll sort of go over that. So let's try to go over this monotonicity. Okay, so we want to compute the difference profile. So let's take 2 points y2 and y1. So the difference profile zy2 is the weight of 1 to y2. So we want to show zy2 minus zy1 is non-negative. So the difference profile is non-decreasing is what we want to show. So what is zy2? So, okay, let's look at this picture. 1 to y2, there is a geodesic. Let's call this as let's denote this by the green path. So 1 to y1, there is also another geodesic. So, and then -1 to y2, there is some geodesic. But just by planarity, you know that this geodesic and this geodesic crosses. So let's call their crossing point as O. They might actually intersect at more than one point, but just fix one crossing point to be O. So we have divided this geodesic into two parts, one before O and one after O, and similarly this geodesic. And similarly, the geodesic from -1 to y1 is denoted by this yellow curve. Okay, so zy2 is the difference profile at y2, which is the weight of 1 to y2 minus weight of -1 to y2. So weight of 1 to y2 is exactly the weight of the green path. You subtract off the weight from -1 to y2, which is purple plus blue, right? So the difference profile at y2 is green minus purple plus blue. And similarly, zy1 is red plus black minus yellow. Okay. So now if you rearrange terms, so we are interested in this difference profile at y2 minus difference profile at y1. So if you rearrange things, you will get this. It's green minus red plus purple. So red plus purple. And similarly, yellow minus blue plus black. Okay. So now let's see that both these terms are non-negative, because green minus red plus purple is non-negative. Why is that? Because green is the geodesic from 1 to y2, and red plus purple is some path from 1 to y2. So certainly the geodesic is the one which has the largest weight. So green minus red plus purple is non-negative. And similarly, yellow is bigger than black plus blue. And that's why this term is also non-negative. So I've written the difference profile at y2 minus the difference profile at y1 as sum of two non-negative terms. And I did not use any randomness here. It's just a fact about geodesic spaces where you have this planarity. Okay, so that's why the difference profile is monotone deterministically. And of course, on average, we see that it grows linearly in this sort of model that we're looking at, but it's always non-decreasing deterministically. Any questions about this argument? Okay. So thus, Z is a random distribution function. So it's continuous because all of the things that we were talking about are continuous and non-decreasing. So it induces a random measure. And we saw that it's typically flat. So which implies that its support or indicates that its support should be a fractal set. So we can ask questions like, what is the dimension of the support of this random measure? And also, because we saw connections to geodesics, we can also ask whether there is a description of the support in terms of geodesics. Because those are the key questions that will drive this stuff. Okay, so this is sort of the first result with Rithi and Alan Hammond last year, that with probability 1, Z is continuous and non-decreasing. So this is not very surprising. We have already discussed this part of the theorem. Z is almost surely locally constant. So Z is a function on R. So it says that almost surely, with respect to the Lebesgue measure on R, it's locally constant, meaning that for every, the function is said to be locally constant at a point if it's sort of constant on an interval containing that point. Basically, it means the complement of the support. And the support of Z, which is a zero Lebesgue measure set, has Hausdorff dimension 1/2. So this random measure almost surely has support which has Hausdorff dimension 1/2. So any questions about the statement of the theorem?
So can I make a question?
Yeah, sure, yeah.
So somehow the only, if you think about geodesics, looks like this coalescing path.
Right.
The only object that I know how to describe very precisely that might be looking at this coalescing path is the Brownian web, no, right?
Yeah, yeah. Mm-hmm. But the paths are of different nature, though. These are different.
Of course.
Yeah.
Of course, completely.
Yeah.
That's my point. It's completely different anyway. But somehow these properties that you're starting to prove look.
Yeah. There are many similarities there, and we will see actually that one of the reasons why this 1/2 comes in is because of some Brownian type properties. Yes.
Okay.
Yeah.
Krishnendu, if you vary the starting points and let that be another parameter, so you have Z is the difference between the ending points, and I don't know, W is the difference between the beginning points. Do you have a description of what you get in that case? And
yeah, so I'll talk about a bivariate case where you're allowed to both vary Y and X. Yes. Is that the question?
Yeah, I think so.
So in this setting, we are sort of varying Y upstairs and sort of going down to -1 and 1, which are fixed points, right? There is another sort of natural setting which is where you sort of look at the weights between X and Y, but you're now allowed to vary both X and Y simultaneously. And so we will see actually a relevant result in that context. Okay. So the previous theorem said that this random measure had support which was almost surely having Hausdorff dimension 1/2. But let's now tie it to the geodesic picture. We saw that in this sort of discussion about coalescence, that when the picture like this occurs where there is coalescence, you get flatness. So it's natural to talk about exceptional points Y upstairs which admit disjoint geodesics to -1 and 1. So typically this is the picture, but there are exceptional situations where the point upstairs admits two disjoint paths downstairs. And let's call that set of points as D. And so with Eric Bates and Alan Hammond this year, early this year, we sort of extended the result with Riddhi to say that the Hausdorff dimension of this set of exceptional points is also 1/2. And actually, the support of this measure agrees with this set of points which admit disjoint geodesics. So these two sets are actually the same. That the support of this random measure and the set of exceptional points admitting disjoint geodesics are exactly the same sets. Actually, this statement actually does not quite appear in the paper, but while preparing the talk, sort of we understood that. But in the paper, what appears is sort of a containment in one direction, but it turns out that they are exactly the same. Okay, so now we have sort of reasonably sort of described this sort of this random measure you get from this difference profile in terms of geodesic behavior, exceptional geodesic behavior, namely the points admitting disjoint geodesics are exactly where the measure charges. Any questions about the statement?
So I have a quick question. So these jumps that you see in your picture, do they correspond to the difference of length of the geodesic somehow?
So what do you mean? So you mean the quality? Sorry, let me just go back to the relevant slide. Maybe that could be useful. This you mean?
Yeah, I mean, you show us a simulation of this increasing process.
Yeah. Sorry, I'm like sorry. My slides are doing something weird, but yeah, exactly. This is a simulation. Yes.
Yeah. So you see these jumps, no? Which
jumps,
are probably not. Yeah. So and the height.
These are not literally jumps. Actually, I mean, like these are so. This is a continuous process. So it's not quite jumps actually.
Okay.
I'm like this is. Of course. The simulation has some discreteness in it, but like in reality, this is a continuous process. So this is a continuous function. And sort of the support is sort of on some fractal set. So you should think of maybe, I don't know, things like Brownian local time or sort of processes like that, which are mostly flat, but then have sort of fractal support.
Mm-hmm.
Yeah, that's basically the picture that you should keep in mind.
So Shirshin, do I have another question?
Yeah.
So if you look at the positive temperature setting,
Uh-huh.
the KPZ equation or stochastic heat equation, if you start out with, say, narrow wedges at two different locations, 0 and 1, you look at the difference in terms of KPZ of the solution at a later time, you won't have quite the same sort of property. You won't have the strict monotonicity, and you won't have the the flatness and the fractal dimension. But I think you do have
you get some additional smoothness, right?
Right, you have differentiability of the difference.
Yeah, exactly. So it becomes I think more smooth in some sense, right? So the Holder exponent.
It's 3/2.
Yeah, exactly. So somehow here you should sort of think of it as an extreme version where it becomes almost flat, mostly, and then there are some exceptional points where you see some action.
Can you somehow see your result coming out of a limit of that type of result for KPZ, or you need something much stronger for KPZ?
I remember thinking briefly about that, and sort of here, sort of the intuition is sort of very based on this sort of geodesic coalescence. I'm not sure how to sort of translate that literally into the positive temperatures framework. But yeah, so I did briefly think about that, but there wasn't an obvious way to sort of get this result out of that. Yeah.
All right, thanks.
Okay. Sorry, my slides are somehow behaving slightly weirdly. Okay. So there is also a bivariate version where you're allowed to, let's say, vary X downstairs and Y upstairs, and look at the set D2 as a pair of all XY, which admit disjoint geodesics going from X to Y. Okay, this is sort of a bivariate analog of the previous setting, and this is maybe sort of related to what Ivan was asking a few minutes back. And again, in this sort of paper with Eric and Alan, we show that this set D2, this bivariate set, also has Hausdorff dimension 1/2. And it turns out that in the one dimension, in the univariate case where the things were only sort of varying in the top in the height 1 sort of upstairs, there was a random measure which was this difference profile. It turns out there is also a 2-dimensional measure associated to this set D2, similar to how there was a measure associated to set D in the one-dimensional case. Okay, so even if you allow points to vary arbitrarily both upstairs and downstairs, the set of points admitting disjoint geodesics still has Hausdorff dimension 1/2. Okay, but we'll mostly focus on the univariate case. The bivariate case, the arguments are quite similar. And it's sort of worthwhile to point out. So there are also related results about exploring fractal geometry in lattice LPP models by Janjigian, Razul Agha, and Sepalainen on understanding sort of. So in the discrete case, of course, if you take finite points, there's of course almost surely a unique geodesic, but you can look at semi-infinite geodesics, and there you can see non-uniqueness. And so these are related to sort of support of Boozman measures, and these are things that have been explored parallelly in related articles. Okay, so I have about 15 minutes left. So I'll discuss some of the proof ideas. And like I said, so I'll only focus on the one-dimensional case. The bivariate case is pretty similar. Okay, so recall the difference profile Zy, which was this difference of the weights. And this looked roughly like this function, monotone, flat, and we wanted to understand the support of this measure. Okay, so we want to prove a Hausdorff dimension of the support. So it's not very important to know the precise definition of Hausdorff dimension for people who are not familiar with that. You can just sort of think of a box dimension where you take small boxes of size epsilon, and we want to look at the number of boxes you need to cover the support. So that's a weaker notion of dimension, but we will sort of just, for the purposes of the discussion of the ideas, we'll just focus on that. So to prove the lower bound, that you need at least as many boxes to cover the support, the key input would be local Brownianity. And the precise form that we use is the one that was developed by Hammond in 2016 related to the last passage percolation in this Brownian setting. Okay, so what is the key local Brownian statement that we want to use? So take some compact set minus m to m upstairs. This is height 1. Take 2 points y and y plus epsilon, which are, of course, at distance epsilon from each other in this compact set. And let's look at the weight from 0 to y and 0 to y plus epsilon. So this difference, so we know that the weight is like a parabola plus some area, right? Area to process. Now, if you look at the distance, which is very small, the effect of the parabola vanishes. If you take the difference, it's a linear function, it vanishes. And so only the effect of the difference of the area between these 2 points is what dominates. And because the area is locally Brownian, you expect this difference to be like square root of epsilon when epsilon is very small. So for our purposes, it sort of suffices to just state this crude bound, although much refined bounds are actually stated in this paper and also subsequently. So what we use is that by some Borel-Cantelli type argument is that the difference of these weights between any 2 points in this compact interval whose difference is epsilon, the weight difference is no more than epsilon to the alpha, where alpha is smaller than 1/2. So fix any alpha smaller than 1/2. Then for all small epsilon, the weight difference is no more than epsilon to the alpha, which in particular says that this roughly is like square root epsilon, where alpha is taken to be exactly 1/2. Okay, so that's sort of the weight, that's sort of the local Brownianity that we will use. So let's see how to quickly prove a lower bound using this property. Okay, so this is the difference profile, Zy. So given any compact interval, we assume that this oscillation estimate is true, which is exactly this thing that I sort of mentioned in the last slide. Now, Z has expected linear growth, right? So if you take some large compact interval, you know that so if you take some, sorry. Yeah. So if you take some large compact interval minus m to m, you know that Z of m here and Z of minus m here, the difference will grow linearly. So, so for very large m, this will be bigger than some constant times m with high probability. Okay. So you have this difference profile, which is locally flat, has at most Brownian oscillation if it has any oscillation, and the growth is linear with high probability. So this is the picture. So you start from here, from minus m, you make linear amount of progress in distance m, but you're mostly flat. So let's see how many intervals are there where maybe it's not flat. So, so this is one interval, maybe this is another interval where it's not flat. This is another interval. So how many intervals are there where it's not flat? So each interval, the weight profile oscillates by at most epsilon to the alpha. So even if it increases, it cannot increase by more than epsilon to the alpha. Okay, but it has to make this much progress. So the number of intervals where you see some action is at least m by epsilon to the alpha, right? Because if you make any progress, it's no more than epsilon to the alpha. You make amount of progress you make is order m. So the number of intervals where you see some amount of action is 1 over epsilon to the alpha times some constant depending on m. Okay. So the number of intervals that you need to cover the support inside this compact interval is at least 1 over epsilon to the alpha. So which indicates that the Hausdorff dimension is at least alpha for any, but this was true for any alpha less than half. So which means that the Hausdorff dimension is at least 1/2. That's sort of the argument for the lower bound. Any questions about this? I mean, it's a fairly straightforward argument given the oscillation estimate that I stated in the previous slide. So you make linear progress on average, but locally you don't make progress more than square root epsilon in an interval of size epsilon. So you need at least 1 over square root epsilon intervals to make that amount of progress that you need to. So which means the Hausdorff dimension is at least 1/2. That's the lower bound. And but again, this is sort of a very sort of innocuous way to define dimension. We sort of just took boxes and covered the support. To formally talk about Hausdorff dimension, one has to go through a general technique, which by now is known as mass distribution principle, which allows you to bound a lower bound a dimension of supports of measures which have some holder type properties. So here the measure has some 1/2 type holder property. And it turns out that there is a general technique that you can use using the heuristic that I described in the last slide to argue formally that the Hausdorff dimension is at least 1/2. Okay, so now let's look at the upper bound. Okay, so we want to look at how many intervals are there y to y plus epsilon, which actually sees some action. We want to now upper bound the number of intervals, which we want to say that that's also no more than 1 over epsilon to the 1/2. Okay. Okay, so if this interval has to see some amount of action for the difference profile, we know that the geodesic from y to -1 and the geodesic from y plus epsilon to 1, they must not meet, because we have already seen that if they do meet, if there is coalescence, then things are flat. So if things are not flat in this interval, we are trying to bound how many such intervals there can be, then a prerequisite is that such a coalescence must not happen. Okay, so you have disjoint geodesics going from y to -1 and y plus epsilon to 1. So it turns out by some geometric arguments, so don't focus too much on this because I don't think I have time to discuss this, but it turns out by some geometric arguments, this non-coalescence picture actually implies a further non-coalescence picture. So it says that here I said the geodesic from y to -1 and y plus epsilon to 1 do not meet. It turns out that that implies deterministically that there is some random x between -1 and 1, such that the geodesic y to x and y plus epsilon to x plus epsilon, they don't meet. Okay, so this picture implies this picture. However, the location of x is random. So x can be anywhere in this interval. Okay, and the proof actually is quite short, but I don't want to get into that because I'm running out of time. Okay. Okay, so this is the situation that we have. Now it turns out that already in 2016, Alan Hammond, in sort of trying to understand other properties of such processes, precisely computed certain sort of exponents which govern probabilities of such events. So it turns out that the probability of such an event happening, that you have 2 points upstairs and 2 points downstairs, both at distance epsilon, which admit disjoint geodesics, this probability decays like epsilon to the 3/2, ignoring some error terms which are subpolynomial. Okay, so this probability is epsilon to the 3/2. Okay, at most. Actually, later we proved that it's actually this sharp, but what he proved was an upper bound. So he proved something like this. Okay, so now once you have that, let's see how to complete the proof of the upper bound. And if there is time, I will come back to how maybe one can prove this bound. But let's pretend that we already have this bound in our pocket, that the probability of disjoint geodesics from points which are very close upstairs and downstairs decays like this 3/2 exponent. Okay, so to finish the upper bound, so suppose you have an interval which sees some action. So we know that that means that there is some random x here where you have disjoint geodesics. So the number of different possible intervals downstairs is 1 over epsilon, because each interval has size epsilon and the distance between -1 and 1 is order 1. So the possible locations of x is 1 over epsilon. Given any particular x, the probability of having a non-coalescence picture like this is epsilon to the 3/2 by this estimate of Allen Hammond. So this implies that the probability that a particular interval sees any action is epsilon to the 1/2, which is epsilon to the 3/2 times 1 over epsilon, okay? So the probability that a particular interval intersects a support is like epsilon to the 1/2, which means if you look at a compact interval, the number of intervals upstairs in total was order 1 over epsilon. Each of the intervals intersect the support with probability at most epsilon to the 1/2, which means the total number of intervals that intersect the support is no more, actually, let's do a less equal to here, is no more than epsilon to the -1/2, okay? And this again sort of then indicates that the Hausdorff dimension, or at least in this case, the box counting dimension, is no more than 1/2. So any questions about the argument? So we took the simple non-coalescence picture, then made a deterministic conclusion that non-coalescence to -1 and 1 actually implies non-coalescence to some random point x and x plus epsilon downstairs. But of course, the location of x can be random. Given any particular x, the probability is epsilon to the 3/2. But just by a simple union bound, the probability that there is some x is at most epsilon to the 1/2, which means that any particular interval upstairs has probability at most epsilon to the 1/2 of intersecting the support. And now you can just union bound over all 1 over epsilon possible intervals, which gives you a Hausdorff dimension up.
I have a question. So you're fixing the y's and you're varying below, and you're asking basically for the event that you have two geodesics that are almost the same and disjoint. So that's, in terms of the line ensemble picture, that's equivalent to the top curve and the second curve coming
exactly
epsilon to each other. But
exactly. That's literally how you get this exponent.
Right. But the probability that two Brownian non-intersecting Brownian motions come within epsilon of each other.
So it's not quite epsilon.
The order.
Yeah, that's epsilon cube. But the point is, because these guys are at distance epsilon, the difference of the weights is actually square root epsilon. So this picture in the line ensemble language is not the two top two lines coming within epsilon of each other, but it's actually coming within root epsilon of each other.
Okay.
Because of the right, so the spatial difference is epsilon, which means the weight difference is square root of that.
Okay.
Yeah, so that's really why you get this additional 1/2. Yeah. Mm-hmm. But yeah, literally, this is exactly how these exponents are derived, by passing to the line ensemble picture. Anyhow, so that's the rough idea behind the upper bound. And I'm running out of time, so I don't think I'll have time to talk about how to relate the support to the set of points admitting disjoint geodesics. So I'll make an attempt in the last 2 minutes that I have. So let's take a point X. So let's try to show that the support is actually contained in the disjoint. Yeah, I'm not sure attempting this now is a good idea. So maybe let's just skip it. Okay, so I'll skip it. And like Ivan was mentioning, the probability of this event being epsilon to the 3/2 is obtained in the following way. So these are 2 points which are very close to each other, whose geodesics are disjoint. So what you can do is they can actually do some surgery to make them tie up to the common point slightly below and slightly above. So now you have 2 different paths, but disjoint, both emanating from the same points actually, instead of 2 different points. And now it turns out that these kind of things actually have a very nice encoding in terms of distant Brownian motion for Brownian last passage percolation. So the fact that you have these 2 disjoint paths, which are almost geodesics, starting and ending at the same point, basically is an interpretation of the following kind. So I'll skip over to the last slide. So like Ivan was mentioning, what it basically boils down to is an event of the following kind. You have 2 Brownian motions, which are non-intersecting. And you want to sort of say that what is the probability that they come within square root of epsilon within each other at a particular given location. And what turns out to be true is that probability decays like epsilon to the 3/2. Why is that? because first you can sort of sample the points in this time point. These are order 1 random variables, so them coming within square root of epsilon within each other contributes to square root epsilon. But now you want them to sort of satisfy the non-intersecting property on this side and this side, and these are independent events. And the probability of each of these events is like root epsilon. Why? So suppose you start a Brownian motion. What is the probability? And suppose you start a Brownian motion from square root epsilon. What is the probability that it hits, let's say, 1 before hitting 0? So that just by sort of Gamble-Swin type arguments is of size, is a probability, the probability decays like root epsilon. So you have a root epsilon coming from the choice of the points on this time axis, a root epsilon for the non-intersecting on this side, a root epsilon for the non-intersecting on this side. So together you get an epsilon to the 3 halves. So that's really the source of this exponent. So I think I'm already out of time, so I'll stop here, and I'm happy to answer further questions if there are any.
Okay. All right. Thank you very much, Shirshindir. There's time for questions if people. Let's all unmute ourselves.
Sorry.
Maybe except for me.
So should I let's maybe stop the sharing of the screen, I guess.
There's time for questions if people want to unmute and ask.
So I have a question. Oh, sorry. You want to ask? Okay, so I have a question because it seems puzzling to me that somehow let's say the geodesic tree starts to look a little bit like this Brownian net, but of course it's very different, no? Because it comes from a totally different.
Yeah, and the sort of fractal exponents are different. Like the Holder continuity of the paths are different and things like that. Yes. Like, so the paths are like not 1/2 Holder anymore.
Yeah, exactly. And but do you have can you extract from these discussions some of the qualitative features of the Brownian net, for example, that the let's say the time that the geodesics need to coalesce and
there are other sort of results, not they were independently developed, where you try to compute the probability of, so suppose you take 2 geodesics and look at the probability of them sort of not coalescing by some time, and what is sort of the power law that governs that. So these kind of things have been developed actually, and so they are quite useful in other applications as well. So yeah, so those results are, so results of this followed kind have been actually developed both in sort of the discrete setting as well as in the Brownian setting to some degree. But of course the picture is much less complete than let's say in the Brownian web. What the Brownian web picture is. Yeah, but yeah, there have been many developments around coalescence, around the fractal geometry. These are some of the sort of more recent results, but the study of coalescence has actually found applications in other contexts, and so for various applications, people have been interested for a long time in trying to understand precisely this question that you asked. Like, if I start 2 points, start geodesics from 2 points which are sort of at let's say distance r away, what is the probability that they don't meet? And let's say look at some semi-infinite geodesics so that they don't have any finite endpoints. And so what is the probability that they don't meet by height t or by height r times something? Yeah. So and what are the precise exponents governing those non-coalescence probabilities have been done. Yeah.
Okay.
I have a question.
Yeah, sure.
So if one wanted to establish the KBZ exponents of 1/3 and 2/3 outside, integrable models, then you need Chatterjee's relation that the 2 exponents chi and xi are chi is 2 xi minus 1, and you also need to know that as you go transversally, that you have these essentially uncorrelated increments roughly.
Right.
And when you combine those, then you get 1/3 and 2/3. So I'm wondering, it's a little bit, it's difficult to see sort of the probabilistic reason why that uncorrelated property holds. Because you have this area limit, and that it's rooted in that when you're looking at the solvable models. But is there a way to see a probabilistic reason why that's true?
Actually, I'm not aware of that. So I'm like also in the discrete setting. So there are these Boosman functions in the integrable world where they turn out to really have independent increments, and so somehow that's not unrelated. But somehow, if you just try to sort of get that picture from coalescence of geodesics, I don't know of an answer, because somehow if you do some very naive heuristics using coalescence of geodesics, then the sort of decay of correlation will turn out to be upper bounded by some power law tail, governed by the coalescence of geodesics. And you don't really see this sort of spatial independence that does turn out to be the case for exponential LPP and also this more other integrable models. Yeah, so I'm not aware of sort of simple probabilistic explanation using geodesic geometry to deduce this sort of spatial independence in the weight profile. Yeah. Mm-hmm.
Yeah. Okay.
Yeah.
Thanks.
Yeah. Mm-hmm.
Any other questions for Shishindu? So if not, let's thank Shishindu and Riddhi for both very nice talks. I'll see you in a week.